Hello, Royals. It's been a while since I've made a new video, but a couple of students pointed out that I was missing a lesson for 1.14 on quadratic systems. So here we go. In 1.14, the curriculum expectation was that we were able to find the points of intersection between a line and a quadratic. And we illustrated how this turns out to be exactly the same as finding, well, the same mechanically as finding the x-intercepts of a quadratic, because finding the x-intercepts of a quadratic is really just like finding a quadratic's intersection with the line y equals 0, isn't it? So if I want to know how many x-intercepts a quadratic can have, I'm used to there being 0 or 1 or 2 x-intercepts or solutions to that equation. It could be predicted by the discriminant. And then in our printed lesson, or if you were in class in 1.14, we discovered that if we're looking for the intersection of a line with a quadratic, we could have 0, 1, or 2 points of intersection as well. I find it interesting our curriculum doesn't go as far as finding the points of intersection between two quadratics, because we're going to notice that it's not going to be much more difficult at all. In fact, in some cases, it can kind of be simpler. Let's say the question says, find the points of intersection between these two curves. I think first thing that we should do is draw a sketch. Let's grab our advice pen. Oh yeah, sketch. To help us visualize the possibilities here. So if we're talking about two quadratics, now these two quadratics are both opening up, but we might even just want to consider two quadratics opening in different directions. Well, look at that. They might not intersect, so we might have 0 points of intersection. Under a couple of special cases, doesn't have to happen at the vertex. You could only have 1 point of intersection. And then as far as homework questions go, this would probably be the most popular orientation. We could have 2 points of intersection. And I think we're going to be able to see why we don't have any other possibilities than, say, finding x-intercepts in grade 10 of a quadratic, or finding the point of intersection between a line and a quadratic in grade 11. This question does say to find the points of intersection, so I'm going to be focusing on this outcome right here. And the way that my sketch is going to help me isn't in predicting what the solutions are, but predicting the format that my solution should take. Okay, if we are asked for the points of intersection, and let's say we trust the question and believe that there's going to be 2 points of intersection, we need to be ready to report 4 numbers in our conclusion. And I'll point out where it's very, very easy to forget to report 4 numbers in a question like this. Okay, so first thing that we're going to do is reason that if these functions are going to be at the same height at the same time, then their outputs have to be the same. I don't think I'm going to find elimination to be a useful approach here, so here's the first step of my solution. I'm going to tell my reader that I'm setting f of x equal to g of x. This is important to communicate because f of x may not ever equal g of x. It's possible that there are no points of intersection, and the purpose of this question is for me to demonstrate or to prove that. So I don't want to write down something that isn't true. I don't want to write down 2x squared minus 12x is equal to x squared minus 4 if it's never true. This is me saying right here, let's see if this could ever be true. Okay. And here's where, although I don't think you'll see any questions like this in your homework, you're going to realize that finding the points of intersection between two parabolas mechanically turns out to be exactly the same as the situations that we practiced, because I have an expression on the left and expression on the right. This expression, because these are quadratics, when I rearrange it into a standard form of an equation, is going to be quadratic in nature. I'm going to set one side equal to 0 because that's how I solve quadratic equations. I'm not going to try to, isolate x. There's too many instances of x. I'm going to do this very, very carefully because any miscalculation can have a severe impact on the intended difficulty of the question. Like, for example, we'll back up in a sec, but for example, this quadratic doesn't have integer solutions. And the purpose of this question was for a student to demonstrate that they know how to find the exact values in simplest form of irrational solutions. If you see these words and you find an integer solution, chances are you might have made a mistake. And sometimes the human brain wants to find integer solutions because they would be easier, but this isn't, we shouldn't just find an answer because it's going to be the easier answer. That shouldn't have an impact on what the answer is going to be. Right, back to the theory behind this. This is a quadratic equation. This quadratic equation, there's no curve here, so we're not finding x-intercepts or anything like that. But this quadratic equation could have 0, 1, or 2 solutions. 0 solutions, only 1 solution, or exactly 2 solutions. Now those solutions would be the x values of the points of intersection. Okay? So I'm going to solve this quadratic equation. This is not a quadratic curve. I'm not looking for the axis of symmetry, the optimal value. There's absolutely no outputs. This is just a quadratic equation. And I know 3 ways. We know 3 ways of solving quadratic equations. We could try factoring. Doesn't look like it's going to work in this case, but it's worth trying. 4 and 1 and 2 and 2. Nope. We could use the quadratic formula, but the quadratic formula tends to give us bigger numbers. And getting exact values in simplest form is harder when we use the quadratic formula. We could solve by completing the square. Now, completing the square can be messy. It's not going to be in this case because we've got a nice even number there. Any other disadvantage to solving by completing the square is eliminated with practice. Students say, oh, completing the square takes too long. Well, then practice and get faster. I'm not good at completing the square. Then practice and get better at it. It is a very good strategy, especially when this number is even. Right here. So I'm going to solve by completing the square. I'm going to complete the square on this trinomial. It's already monic. That's great. I'm going to draw a little square because I always draw squares when I complete the square. I have an area of x squared, the area of -12. X has to be split evenly, so each one of those would have to be -6. I now know the dimensions of my square. This is going to be part of a square that has dimensions x minus 6 by x minus 6. That means that to complete the square, I am going to add a square whose dimensions are -6 by -6. I'm going to add 36. I can't just add 36 to complete my square. I have to maintain equilibrium, so I subtract 36. Like that. The alternative is I could have added 36 to the other side. That's an interesting approach when you're solving an equation by completing the square, but if you're completing the square for a quadratic function to get a function into vertex form, you might want to stick with this traditional approach. Here's my square of dimensions x minus 6 all squared. And then I collect these terms right here. -32 equals 0. Okay. In this example, the numbers aren't as small as possible, or as small as they will be in all other cases. I'm adding 32 to both sides, because right now all I need to do is not use some fancy formula that I have to remember. I'm going to solve this kind of like a linear relation. I'm going to undo operations in a reverse BEDMAS order. I add 32 to both sides, take the square root of both sides. I have my sketches to remind me that quadratics can have more than one solution, plus or minus root 32. And here we go with the exact values in simplest form. When the question says exact values in simplest form and show I'll work by hand, that doesn't mean show me what your hand is doing on your calculator. It is not calculator time. Get rid of the calculator. Right? To get full marks to convince me that you're doing this by hand, show me the simplification of root 32. 32 is not a perfect square. 32 is an even number. Ooh. 32 has an even square factor, a very large even square factor of 16. 32 can be tricky because you can remove 4 twice, and 4 is a perfect square. If you do prime factors, smallest prime factors first, you tend to hit your greatest square factor first. So off on the side here, let's say root 32 is root 16 times 2, which is root 16 times root 2, which is 4 root 2. So this becomes x minus 6 equals plus or minus 4 root 2. And x equals 6 plus or minus 4 root 2, like that. Okay. I'm going to do a little detour here, just again to try to convince you the quadratic formula is not the way to go here, but let's just point out we're not done the question yet. We now have the x coordinates of our points of intersection. We're more than halfway through the question, that's for sure. But we still have more work to do. Okay, and this is where it's so easy to stop, because in grade 10 we solve systems and we get 2 answers, and this looks like 2 answers. In grade 10 we solve quadratics and we get 2 answers, and this is 2 answers. In grade 11, we find intersections of curves or lines with quadratics. And we get 2 points of intersection, which means we need to report 4 numbers. If you draw a sketch, you'll never forget to report those full numbers. Well, you'll forget less often. Okay, do I have another color? Looks like the pencil's out of ink. I could use a different type of blue pen and it might show up a little bit different. Yeah, real different here. Let's just see what would happen if I use the quadratic formula on here. I would get x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And I mean, if I'm working by hand, then I'd have to square negative 12. That was in my multiplication tables in, I don't know, grade 4 maybe? So hopefully I still know those. Then I simplify 144 minus 16. Let's see, if I subtract 20, I'd be at 124. 4 higher than that, 128, I guess. Oh, sorry. Now, notice some of the dangers in taking this approach. It is very easy to accidentally divide the 12 by 2 and not divide the root 128 by 2. Okay, we would have to use the distributive property of division. Both of these are supposed to be divided by 2. Problem is, this isn't a 128. Half of the square root of 128 isn't the square root of 64. That's very, very silly. The square root of 64 is an integer. The square root of 128 isn't, so how could 128's square root divided by 2 be an integer? No, now I have a bigger number, 128, and I need to simplify it, and I'm expected to simplify by hand. That's going to be, what, 64? Well, that didn't take that long, I suppose. So then I write the square root of 128 is going to be the square root of 64 times 2, which is going to be root 64 times root 2, which is going to be 8 root 2 over here on the side. Then I get x equals 12 plus or minus 8 root 2 all over 2. And then I see that my numerator has a common factor shared in the denominator. And instead of trying to divide across here and making mistakes, I'm always going to factor. It does take me a little longer. And I get x equals 6 plus or minus 4 times the square root of 2. Did I get all that on camera? Fine. This is, again, why grade 11 university teachers will argue with students that say the quadratic formula is easier. It's really not. It takes longer. It makes your numbers bigger. It's the argument is it's harder to learn a new method. That doesn't mean that the new method is harder. You put in the effort now, and this will be much easier for you. Look, my numbers stay smaller. In a lot of questions, this radicand will already be reduced. I chose an example on purpose where we had to reduce, because sometimes students that solve by completing the square forget to reduce their expressions, and we should always be trying to reduce. So, okay. Solve by completing the square if possible. Okay, we still need to finish this question, and the added challenge here in the printed lesson, or in class for lesson 1.14, we mentioned that it is a very good idea to substitute these expressions into the linear relation, because it's going to be the simpler relation to use. In our question, we don't have an option. We have to substitute into the quadratic. And I mentioned in class, if you were there, that this is something we're going to have to do eventually anyways. So it's your choice into which expression you want to substitute. I think that it would be simpler into g of x, so let's try that out here. I'm going to substitute in, let's do the positive pathway first. Let's tell our reader we are finding g of 6 plus 4 times the square root of 2. Sorry, I'm trying to show both on the camera. There's g of x. So this is going to be my argument squared minus 4. My argument is 6 plus 4 root 2. Now, there are a number of major mistakes that we can make here. Major mistake number 1, I suppose, would be thinking that 6 plus 4 root 2 is 10 root 2. And this is 6 wholes, and then I'm adding 4 root 2's. Next major mistake would be writing something like 36 plus 16 times 2 or something like that, just distributing the exponent through. That is not how exponents work. We showed that here with the square. X minus 6 squared is not x squared plus 36 or x squared minus 36. Now, you should treat this like grade 10 algebra, and in grade 10 algebra, your teacher probably recommended that it's a good idea to write this, these factors out twice, so that you can see the distribution. I might actually go back to an area analogy here. Sorry about the bouncing, folks. To try to convince you. We have a square that has dimensions 6 plus 4 root 2 by 6 plus 4 root 2. There's going to be 2 squares and 2 rectangles. This square is going to be 36. This rectangle is going to have an area of 24 root 2. This rectangle is going to have an area of 24 root 2. And then this is going to have an area of 4 root 2 squared. That's going to be a 4 times a root 2 times a 4 times a root 2, which is a 4 times a 4 times a root 2 times a root 2. And a root 2 times a root 2 is a root 4, which is a 2. 1632. Yeah. So when I expand this, I might not show my square every single time, but you can. Maybe I'm just doing 6 times 6 is 36. 6 times 4 root 2 is 24 root 2. 4 root 2 times 6 is 24 root 2. 4 times 4 is 16. A root 2 times a root 2 is a 2. And then I have a minus of 4. And let's tidy this up a little bit and get, I don't know, what do we have here? 36 minus 4 is 32, plus 32 is 64. And I have 24 root 2 plus 24 root 2, which is going to be plus 48 root 2. Okay. You could spend a lot longer on this question as well. You could double check this into the f function. You might want to try that on your own and make sure. I guarantee this is the correct value. So f of 6 plus 4 root 2 should also be 64 plus 48 root 2. You could also then substitute in g of or f of 6 minus 4 root 2. But as we discussed in class, because of the symmetry here, you can probably predict what's going to happen without showing the substitution here. Let's just predict some of this. I'm going to get 36. I'm going to get minus 48 root 2, but then another plus 16 times root 2 squared, which is 32. And then I'll have a minus 4. So we should be able to predict. You see the 36, 32, 64 again. The only difference tends to be one of these signs when I substitute in an expression that has a different sign there. So, to conclude, the points of intersection are, let's see, an input of 6 plus 4 root 2 partnered with an output of 64 plus 48 root 2. That's 1 point. A point is an ordered pair. It's an input and an output. And the other one was 6 minus 4 root 2, comma, 64 minus 48 root 2, like that. Okay. The question is a little bit more difficult than our curriculum level, just because we don't need to have 2 quadratics, so having the ability to substitute into a line will make things a little bit easier. Check out question number 7 on 1.14 for some excellent test practice here. Try it out.